Hello, welcome to Engineers Mindset. Today I'm going to take us through a series on thermal or temperature stress. What is thermal stress? Just like the name implies, thermal simply means temperature or heat. Okay, so thermal stress is simply the stress that is found or deduced in any material whenever that material is subjected to a high level of temperature or any form of temperature or heat at all. The stress that is formed on a material when the material is subjected to temperature is called the thermal stress. Alright, just like you all know, stress and strain always work hand in hand. Alright, so if I subject the material to temperature, not just stress is induced in the material, also there's a change in length with respect to the original length of the material. That change in length with respect to the original length of the material is called the strain of that material. And since that material is subjected to temperature, then that strain is also called a thermal strain. Now, every material has what is called thermal expansivity. The thermal expansivity is simply the property of every material which determines how fast a material responds to change in temperature. So if I subject any material to temperature, the material has the ability to melt faster or slower. That property that helps the material to melt either faster or slower is what we call a thermal expansivity of the material. So every material actually has that thermal expansivity inherent in them. Okay, let's take for instance, I have a copper rod. Okay, and I subject this copper rod to different levels of heat. Alright, now this copper rod has a thermal expansivity. Let's use alpha to represent the coefficient of thermal expansivity. Alright, the original length of this copper rod is simply L, so you can simply call the length L. Okay, let's take it up here. The original length of this copper rod is simply called L. It has the length of the copper rod. Now, if I subject this copper rod to heat, after some time, it melts, and of course, there is going to be an increase in the size of the length. So there is going to be a change in the length, an increase in the length of this material. So let's call this the increase in length. So let's call that change in length, which is increase in length. Okay, so there is bound to be a change in the length of the material due to what? The heat applied to this material. This change in length is a function. Now, before the change in length, the material actually has, or this copper actually has what is called an ambient temperature. Ambient temperature is simply the initial temperature of every material, the temperature of every material at room condition. That's what is called an ambient temperature. Okay, so the material actually has what is called an ambient temperature. This ambient temperature can be called the initial temperature of the material. So simply T1 to represent the initial temperature. Okay, initial temperature. So we can simply use T1 to represent the initial temperature. Now, when we subject this material to heat, the heat has a different level of temperature itself. That level of temperature is what we call the final temperature. So you can call it final temperature, which is T2. Okay, final temperature T2. Alright, so the ambient condition of temperature for the material is simply T1, while the final temperature is simply the temperature of the heat which you're subjecting this material to. Now, the change in length, this change in length experienced due to the heat subjected to this material is simply given as change in length. Okay, is simply given as the product of the thermal expansivity, which is alpha, and the change in temperature, which is T2 minus T1 times the original length of the material. Okay, so the change in temperature of that material is simply the product of the thermal expansivity of the material and then the change in temperature and then the original length of the material. Okay, so the change in length of the material due to the heat applied to the material is a product of the change in is a product of the thermal expansivity and the change in length, change in temperature, and the original length of the material. So we have this. So we can simply say that change in length is simply alpha times T2 times T1 times the original length, where T2 minus T1 is called change in temperature. So I use delta T to represent change in temperature. Okay, change delta T is simply T2 minus T1. So we can replace this equation by simply saying that change in length is simply thermal expansivity times delta T times original length. Let's call this equation 1. Now, recall that if I divide equation 1 by original length, so let's say I divide equation 1 by original length L, I'm simply going to have change in length all over original length, and that's equal to alpha times change in temperature, okay, times change in temperature. I'll simply have this. If I decide to divide this equation by original length L, I'm going to have this equation. Alpha stands for thermal expansivity, change in temperature. Alright, now notice that recall when I talked about stress-strain relationship, please do well to look up the stress relationship videos if you've not gone through for proper understanding. I define strain as simply change in length all over original length. Okay, so strain itself is simply the change in length with respect to the original length of the material. So we are simply having change in length all over original length. So it simply means that this equation stands for what is called strain. Okay, so therefore I can replace this as simply what? Strain is equal to alpha times change in temperature. Call this equation 2. Equation 2 stands for what is called the equation for thermal strain. Okay. So can this see if you represent that? So that's the equation for thermal strain. So the thermal strain of every object is simply the product of the thermal expansivity of the object and the change in temperature. That is called thermal strain. Okay, so if this is thermal strain, recall that when I talked about stress-strain relationships, please do well to look up the video. I also said that Young's modulus is simply, I said that Young's modulus, which is E, is simply stress all over strain. So it means that I can make my stress subject to the formula. I will have stress to be simply Young's modulus times strain, or strain times Young's modulus. So if this is the case, then thermal stress is simply thermal strain times Young's modulus, and therefore thermal stress is simply thermal strain equals alpha times change in temperature times Young's modulus. Equation 2 is actually the equation for thermal stress. Okay, that's the equation for thermal stress. So thermal stress is simply thermal strain times Young's modulus of the material, and the thermal strain itself is simply the product of the thermal expansivity times thermal expansivity and change in temperature. Okay, so once you multiply that by Young's modulus, we obtain what is called the temperature of thermal stress. Alright guys, now we talked about situation where it's just an individual bar. So what happens when we have two or more bars joined together and then subjected to temperature? A different thing happens together. If two or more bars are joined together either by welding or by bracing or even by a screw or thread or whatever means they are joined together and then subjected to temperature, something different occurs, and I'm going to show you what that is in this video. Alright, so let's say we have more than one bar subjected to temperature or heat. For instance, this is now a copper and a steel bar. This is forming what is called a composite bar or a compound bar. Now these two bars are actually subjected to heat. And since they are joined together, it means that they are supposed to melt at a certain proportion. First of all, one of the materials has what is called a higher. I've said that thermal expansivity is simply an inherent property in every material, which helps the material to respond to change in temperatures, either faster or slower. So these materials now have different thermal expansivity. Of course, copper has a lower thermal expansivity compared to steel. So it means now that copper will melt faster than steel. The higher the thermal expansivity, the higher the ability of the material to melt faster. Okay, so the material with higher thermal expansivity will melt faster than the material with lower thermal expansivity. So let's use alpha H to represent a higher thermal expansivity. H stands for higher. And let's use alpha L to represent lower thermal expansivity. So L stands for lower. So the copper has the higher thermal expansivity, while the steel rod has the lower thermal expansivity. Now the copper and the steel are joined together and then subjected to heat. What happens is this. Two things actually play. But before we talk about the two things, let's start analyzing the melting capacity of these materials. Since copper has a higher thermal expansivity, it means that copper will melt faster than steel. Meanwhile, steel has a lower thermal expansivity. Steel will melt. But at the end of the day, the two materials are joined together. They are welded together. So what happens is that copper will melt to a certain point when the melting point is complete and wait for steel to melt up to that point. Now, due to the process of melting, there is normally an increase in length or decrease in length, whatever. That will give us what is called the thermal strain, as seen in the previous equation, that's equation 1. We obtain the thermal strain in equation 1 due to what? When it is subjected, there is bound to be difference in length with respect to the original length. That difference in length with respect to the original length is what we call the thermal strain of the material. Okay, so that same thing employs here or exists here. When copper melts first or faster to a particular point, it waits for steel to also melt till it gets to that point. Now that point where the two materials completely become liquid is what we call, that point they have what is called a common strain at that point. So we call that a common strain. The point where the two materials melt. So we simply use this symbol, which is for strain, to represent the common strain. Okay. Meanwhile, let the strain of the higher material be strain of higher material, or let's use strain of copper to be this. So we C, while strain of steel. Okay. Alright, so there is representative for copper and this is for steel, and this is the common strain. The common strain is the point where the two materials completely becomes liquid. So the material with higher thermal expansivity melts to that point and wait for the material with lower thermal expansivity also melt to that point. For that reason, the strain of copper, which the material that has higher thermal expansivity will become strain of copper. Is simply the higher thermal expansivity of copper, which is higher thermal expansivity, times T2 minus T1, which is change in temperature, okay, minus the common strain. Okay, so this represents the common strain. The common strain is that point in which the strain of in which the materials completely melts. So the copper has the higher strain than the common strain because it melts to the common strain faster than the material with lower thermal expansivity, which is steel. Okay, that being said, the strain of the steel becomes the common strain minus the strain of steel, which is alpha lower, which is thermal expansivity of the lower material, which is steel, times change in temperature T2 minus T1. Okay. Now, since the common strain is greater than the material that has a lower thermal expansivity, then the material with lower thermal strain of the material with lower thermal expansivity simply represents this. Where this and this represents the common strain. The common strain is that point, or the strain at that point where the two materials completely melt. So that becomes the common strain. Now, the total strain for these two materials that are joined together, total strain is the sum of strain of copper and strain of steel. Okay, so total strain will simply give us the strain of copper plus the strain of steel, and that's equal to strain of copper gives us alpha higher times T2 minus T1, okay, minus the common strain, while the strain of steel is simply this, so plus strain of steel plus the common strain minus alpha lower times T2 minus T1. Alright, so that gives us the sum or the total strain between the two materials. Okay, so the total strain of copper plus strain of steel is now equal to, of course, the common strain and this one cancels out. So what we have is simply the thermal responsibility for the higher material and the change in temperature T2 minus T1. Okay, minus thermal responsibility of the lower material and the change in temperature T2 minus T1. And of course, by factorization method of Laplace equation, we can simply factor this out. I'm going to have the strain of copper plus the strain of steel is simply equal to, if you want outside the bracket, we're going to have thermal responsibility for the higher material minus thermal responsibility for the lower material, okay, times the change in temperature T2 minus T1. Call this equation 3. Now, equation 3 is used to determine the strain of materials or compound materials that are subjected to temperature. When a compound bar or a composite bar is subjected to temperature, this gives us the sum of the strain. The strain of the first material plus the strain of the second material is simply equal to the thermal responsibility of the higher thermal responsibility minus the lower thermal responsibility times the change in temperature. That gives us that equation. Okay. Now also recall that we said that strain is simply stress all over Young's modulus. Okay, if strain is simply stress over Young's modulus, it means that I can rewrite equation 3 in place of strain of copper and strain of steel. I will simply have let me take it down there. I will simply have, in place of strain of copper, I will have the stress of copper all over Young's modulus of copper plus the stress of steel all over Young's modulus of steel. That's equal to same thing, alpha higher minus alpha lower times the change in temperature T2 minus T1. So call it equation 4. Alright, so equation 4 and equation 3 are also the same equation, but a modified approach to it. So I can write strain as simply stress all over Young's modulus. So if that is the case, then you can also call this equation this. The both equations are the same. Alright, so the first thing that happens when compound materials are subjected to temperature first is the ability to determine the strain. Notice that there's a common strain. Common strain is simply the point where the two materials come to completely melt. The material with higher thermal responsibility has a higher common strain, a higher strain than the common strain. So we have this. So we usually subtract the common strain from the material with higher thermal responsibility, which is copper. Okay. Meanwhile, the material with lower thermal responsibility has a lower strain compared to the common strain. So we subtract this strain from what the common strain, which is this. And if we sum the two strains together, we are going to have this equation. And this equation represents the strain of two materials subjected to what? Two compound bars that are subjected to what? Heat. This gives us the equation for the strain. Now, the second thing that happens on the two bars that are subjected to temperature, second thing that happens is that the material that has a higher thermal responsibility will exert a push while it is melting or while it is expanding. Please take note, when I say expanding simply means melting, ability of the material to melt whenever temperature is applied to it. That's expansion. Okay, so while the material is expanding, the one with higher thermal responsibility is expanding, it exerts it pulls the material that has the lower thermal responsibility below. It pulls it to expand at its own rate. Meanwhile, the material that has a lower thermal responsibility knows that it has a lower thermal responsibility, and therefore it cannot expand at the same rate as the material with higher thermal responsibility. The essence of the push or the pull is simply because they are welded together. So what happens is this: as the material with higher thermal responsibility is exerting a pull on the material with lower thermal responsibility so that they can also expand at the same rate, the material with lower thermal responsibility will exert a push on the material with higher thermal responsibility, saying, look, I don't have the same expansion rate as you. As such, I cannot expand in the same manner as you. Okay? Now, for equilibrium, the pull exerted by the material with higher thermal responsibility is equal to be pushed exerted by the material with lower thermal expansivity. Now, this pull and push are simply called force. So we're simply going to use, P lower or P higher represents the pull on the material with higher thermal expansivity. And we said it is equal to the push by the material with lower thermal expansivity. So pH equals PL, that's for F going to be achieved. The pull and the push are always equal. Now, this pull and push is simply what is called force or load in strength of materials. It's simply called load. Now, recall that we said stress is simply force or load all over area. So if stress is load over area, it means I can simply make load solved by the formula, and it's simply going to be stress times what? Area. Okay. Now, relating this to this material is simply a copper material and a steel material. So in this case, what we are simply saying is that the load on the copper is equal to the load on the steel. That's what we simply see. Material with high thermal expansivity asserts a pull that is equal to the push offered by the material with lower thermal expansivity. So since the two materials involved there are copper and steel, then simply the load on the copper is equal to the load on the steel. And in that case, since load is simply stress times area, it means that I can write this equation to what? In place of load of copper, I can simply have stress of copper times area of copper, and that's equal to stress of steel times area of steel. So call this equation 5, call this equation 6. Alright? Basically, these two equations, equation 3 and 4, and equation 5 and 6 are the basic equations that govern temperature stress. Alright, so we are going to now use these equations in the next video to start our analysis in thermal stress and strain. Alright guys, I hope you enjoyed that video. If you do, please, I would like to hear your comments, your thoughts in the comment section, and of course, like, subscribe, and of course invite my friends to the channel. Thank you very much. I will see you in the next video. Cheers.